All right, good morning. So first is, I guess, what's on quiz 2. So quiz 2 will not be, won't have anything that's on quiz 1 because you've already done that and we've all done fairly well on it. So this will all be processes, locks, threads, all that fun stuff. Probably some stuff involving exec, wait, and then threads, maybe a little bit about signals, but that's pretty much it. But based off that, that's a lot of questions you can ask because that gets confusing very quick, especially if it's your first time. So that's why we introduced it way before let, set, and now we can play around with real examples and kind of argue about it. Because in the real world, it's not always super obvious and there's always going to be some trade-offs. So let's go. So I like doing actual examples, so that's what we'll be doing today. So we know enough about coding. We can successfully run a bank. So let's do some financial code. So let's assume we are running a bank and we're doing 100 million transfers, which isn't that many. So I wrote a little simulation that can create a varying number of accounts just to see how it affects things. And each account has a unique ID associated with it and then a balance. And every account starts with $1,000. So when we're running our simulation, our 10 million transfers, they're just going to randomly pick 2 accounts to transfer money between. And whoever gets picked to send money will send 10% of their total balance to the other person. And that's it. So you're just going to send 10% of your current balance, which should subtract that from your balance and add it to someone else's balance. And then just to make things, I guess, a bit more realistic so that times actually make sense, there's a securely connect to bank function we have to call before starting a transfer, and essentially it's just going to waste some time. So that's it. We're now going to just go over the question. We'll have data races and deadlocks because we want to parallelize the bank transfers, and we'll see why we end up in this situation. But this is essentially going to be like half the quiz covered in this one example. So our goal is to be faster than 11 seconds. If you want to find the template, it's in lecture 17 in the examples repository, and this is how you compile it and run it. There's a typo because that should be lecture 17, not 16. And then to run the program, you just run the bank sim. So let's go over it real quick. So again, we're simulating, what is it, 100 million transfers. So let's see how long it takes. So say we just have 1,000 bank accounts. So if there's 1,000 bank accounts, they have $1,000 each. That's a total of $1 million we're managing, small bank. And at the end of all the transfers, what should the balance of the bank be? $1 million. So we shouldn't lose money by just transferring. The transfers are all a zero-sum game. So if I do that, I'm just printing out how much memory is used for the accounts because it will become an issue if I have too many accounts. But here we have $1 million, and at the end of all the transfers, we still have $1 million, and it took about 11 seconds. So let's read the code. For those coming in, we are running a bank. We have a bunch of accounts that have money, and we're simulating 100 million transfers between the 2 accounts. So let's look at the code. So there's a starting balance and number of transfers, and we're going to make this thread, so that's why I have it defined for that, and I'll use it later. So here's the struct that represents an account. It has an identifier, and it has a balance. Makes sense. And then here's a function we can ignore that simulates connecting the bank. Here's our transfer function. So it's already picked an account to send from and then to. So we have to securely connect to the bank. And then we figure out the amount we have to transfer, which is just 10%. So we just divide the current balance by 10. And it's integer division, so it can round down. And that way we don't send negative money or anything weird like that. And then we subtract the amount from the from account and then add it to the to account. So zero-sum game here. And then that is our run function that we don't have to care about. And then in main, it will make sure we have an argument. So it's the number of accounts we should have. This just parses the number, turns it into something we can actually use, like an unsigned int, and then allocates it. We say how much memory we're used. And then right here is where we initialize everything. So each account gets its own unique ID that starts at 1, just because most things just start at 1 and don't have an ID of 0, and then sets the starting balance. So everyone starts with $1,000. So then if I know everyone starts with $1,000, I can just calculate what the bank's initial funds are. It's the starting balance times the number of accounts that we have. So this is code we'll use later. And then this is the loop we want to parallelize. So this simulates all our transfers. So for the number of transfers, so 100 million, we generate a random from index and then a random to index. And then we just call that transfer function we saw before that actually does the transfer. Then afterwards, this is our sanity check to check that the bank still has the same amount of money it started with. So total balance is 0, and it just sums up every single account's balance, and hopefully we didn't lose money. Otherwise, that would be really, really bad. Our bank would probably be doomed to failure at that point. And we just print out what the final funds are. Make sense to everyone? Okay, so if I want to parallelize this loop and make my bank run faster, what should I do? Threads. Yes. Okay, so I want to parallelize this loop. I'll comment it out. So we want to make threads. Would it make sense to make processes instead of threads? Why? Yeah, there's going to be a lot of communication because the amount depends on the current bank balance, and they're not completely independent. So if you split off, an eighth of the transfers in each process, they might have outdated data because one might transfer money out of an account, and then if another process transfers money out of that account, they're all independent. They would have to, they would have wrong values. And to make them right, you would have to communicate at every step, so every process updates it, and all that communication has to go through the kernel, which is going to be slow. You have lots of communication, so it's just not going to be worth it. You can do it, but it's going to be slow as dog. So we're going to use threads because they're all in the same address space. We get sharing by default. It's all nice and quick. So this is the loop we're going to parallelize. We want to make threads, so I saved myself some typing and wrote this. So in this, we're creating num threads, and then for each num thread, we're just creating it. So I want to pass in some thread ID just to show passing data to a thread, and also it's going to be somewhat helpful. So I just create memory for an int, an unsigned int, and then malloc it because I don't want to pass anything like a stack address or anything because it's going to be invalid. We share stacks. Doing something like that would be really, really bad, and we saw an example of that before. So I'd have to malloc it, and then I set the value of the memory equal to I, and then I pass it as part of pthread create. So first argument is the pthread, so it's whatever thread I'm creating. I'm giving it default argument, so it will be a joinable thread, not a detached thread or anything like that. Then I'm going to say it should execute this run function, and this is the pointer argument I'm giving it. It's the pointer to my thread ID. And then after I create all the threads, my main thread just joins all of them. So it waits for them all to finish. So at this point, all my transfers should be done. So any questions about this? Okay. So then the question is, what should be in my run function? So right now my run function just gets so the argument we passed in, we know it's a pointer to an int. So we just cast that argument and then dereference it to get its value, and then we free it, so we're all good. So we're good people. We're always freeing all of our mallocs. Okay, so what should be in this run function? Wait, 100 million transfers.
Would each thread just want to do that divided by how many threads?
Yeah, so, right, I'm trying to parallelize everything. So instead of having one thing just do 100 million, I can just divide up the work between each thread. That seems like it makes sense. So we can just, we can copy pasta a little bit. That's everyone's favorite programming technique. I know it's mine. So instead of doing num transfers, should be wrong because this is every thread doing all of the work. So this wouldn't be any faster. So how many times should it go through? Divide by 8, or if I want to give it a nice number, I can say num transfers, I even call it per thread, equals num transfers divided by num threads. It's a little more readable. And then in here, I would do num transfers per thread. Yeah.
I don't know off the top of my head, but let's say we have a num. What if that results not an integer, so you might make less than 100 million? Is that still okay? Or?
Yeah, so in this case, I'm assuming that it divides evenly. If it doesn't divide evenly, you could take the mod of that and then just set off, you do an extra, you do an extra, you do an extra, and it's mostly balanced. But in this case, it divides evenly. But if you want to be like super pedantic about it, yeah, you could take the mod. I had that in there originally, but it just made it harder to read. But yeah, if it didn't divide evenly, you'd have to do something about it. Okay, so cool. Now I have 8 threads. They're each doing an eighth of the work. Should be 8 times faster, right? No. Mess with each other. So do the threads mess with each other?
Well, what if 2 are trying to transfer to the same account or something?
Yeah. So what happens if 2 are trying to transfer to the same account? It's a data race and computer dies. Yeah, if your computer died, none of our computers would ever work. So, well, let's just run it and just see for fun what happens. So each thread's doing an eighth of the work. It should be about 8 times faster. Let's simulate it. Takes like 11 seconds before. It's a bit faster. But we lost some money. Yeah, it's taxes. Yeah, but you're the bank. You're supposed to be gaining money, not losing it. Well, let's see. So I lost money because of data races, probably, because what you said before, we could be transferring to the same account. So if I have less accounts, will that be better or worse for data races? Worse. Why?
The amount of potential transfers is lower, so you might have more threads targeting the same transfers.
Yeah, if I have less of accounts and my data races are between accounts, if I have less of them, it's just more of a chance for more data races and more collisions. So let's try it with 100 accounts. Should come back. I gained money this time. Well, let's try with 20 accounts. So 20 accounts, my bank, I'm a little small bank. I have 20 grand.
Infinite money glitch. Wait, why is this a problem?
Why is this a problem? Because the bank would probably actually only have 20 grand in cash, and now it says it has 122,000. And if you loan that out, you don't actually have that money, and then we're like 2008 financial crisis all over again. But yeah, let's try it a few other times, because some results are really, really fun. Okay, that one wasn't too bad. 2 accounts? Okay, 2 accounts. Oh, we gained a lot. Let's do 2 accounts. So we have this is a really weird bank that only has 2 customers, but let's go for it. Oh, yeah. So is that normal? So what likely happened in that case? Where I created, more money than the world has to offer. Yeah.
The transfer continuously like switching context, so like the same process was being done multiple times.
Yeah, so it's like pretty much just transferring between accounts, and there's being lots of context switches all doing it. And eventually, it's probably going to subtract more money than it actually isn't that read from the account originally. And because it's an unsigned int, it would underflow and then go back to the maximum and then kind of look like that. So that would be very, very bad if your bank shows up with that, which if you've like, what is it? What Reddit subreddit? Is it like programming Gore or something like that? I've seen bank accounts that, or like bank statements that look like this, or no, it was like a medical bill that looks like this. So after this course, you guys shouldn't be doing this. Okay, so it's also not, we have data races and it's also not quite 8 times as fast. So that's kind of weird because the transfer, this just wastes the same amount of time every time. And then these are just a few operations that should like perfectly parallelize. We should get 1/8 of the time. Then the only other thing that might be going on is we call RAND. So are there data races in RAND? So now when you've multiple threads, you have to argue about everything. So you wouldn't know the implementation of RAND, so you'd have to look it up. That is not a helpful documentation. That's more helpful. Okay, so this is RAND. Let's see what it tells us. RAND returns in the range 0 to RAND max inclusive, blah, blah, blah. So it tells us it is thread safe and multi-threaded safe. Like it's safe to call with multiple threads. So it doesn't have any data races, probably because it locks, but you would know that the random number generator has some state in it or something like that. So it's slowing down because they're all using the same state and all the threads are fighting over that state. And because it's thread safe, it's essentially going to make that part sequential. So we're not going to get our kind of ideal speed up of being an 1/8.
Doesn't mean RAM is atomic?
It is, it kind of looks like atomic because it's going to be thread safe, so it doesn't matter in what order you call it in. So you can kind of think of it as atomic, but it's not, it's a bunch of atomic things that happen together in like a critical section. But for argument's sake, you could think of it as kind of being atomic. Is that true? Yeah.
Is there a way to give each thread its own random?
Yeah, so this is beyond this course, but we have free time, so we can essentially give each thread its own RAND and make things a lot faster. So in this, if we read the description, blah, 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 RAND-R is a generator where it takes a seed argument that stores the state, and it's essentially all independent, and it's all of its state. So we could use RAND-R instead, and that would be nice and independent. So we can do that. It takes a seed. So we can just set the seed equal to thread ID +1 or something like that. Who cares? And then instead of RAND, we'll use RAND-R, and all it wants is a pointer to some value that it wants to modify. So now we change it so that RAND's all nice and independent. So if we do that, and this is like beyond this course, we won't have to argue about, but when you actually do this stuff, if you have threads and you call functions, you have to argue about them. So you have to like check, can I call this? Is this thread safe? Et cetera, et cetera. 10 was fine. So if I run this now, it's way faster. So now it's kind of close to that ideal speed up because now each thread's actually independent. So they're not waiting on each other whatsoever. Previously, they were waiting on each other for RAND because it had some shared state. Now, we're all good. Everything's nice and independent, except we still have that problem where, oh God, we have a lot of money now. So how do I want to fix this problem? Locks. Yeah, so I can fix the problem by eliminating data races. Locks are a good way to do that. A mutex is a great way to do that. So I should create a mutex? Let's all create a mutex. All right, I created a mutex. Oh, so, and then in here, there's no data races in here because this just gets a random number. It's independent. This gets a number. It's independent. Calling transfer, that's where the data races actually happen. But I don't have to argue about data races in run anymore. So as long as transfer is OK, I don't have to argue about run. So actually, I want to move the lock up because transfer is where my problems lie. So now I have a mutex. Where should I put it? Yeah.
Is securely connect critical, or can each thread do that?
Each thread can do securely connect independently.
After a mount, and then there's right, like in between, yeah, that line and the next, and then after.
Here?
Yeah. I lied so hard. Wait, before that. Shoot, that line before that.
You lied.
I lied.
Okay, let me just finish typing it. So you want to move it up there? Okay, where's unlock it where? After this line? We agree? No. After what?
55.
After 55. Yeah, so there? Okay, cool. So do we have data races now? We shouldn't? Come on, we can be more confident than that. We don't have data races because all of our races were on some account's balance, and now we only access the account's balance while we have a mutex, which means there's only one thread there at a time, which means we can't have data races because there's not two concurrent accesses, there's only one at a time. So, should we have any data races now? No. So let's do something like that. Wait, run it again? So we don't have data races. Are we satisfied? No, it's pretty slow now, too. More threads. Okay, well, first, we also didn't demonstrate something else, too, where sometimes this might not be a problem or you might not recognize it. So this is our nice data racy version because we removed the mutex. Well, if I'm, Wells Fargo or some crappy bank and I'm too big to fail, I have $10 billion, all good. There's so many accounts, I don't ever see the data races. So you can be too big to fail. It's like the real world, right?
Can you explain why randr is helping again?
So randr just has state, just modifies that seed variable, and that's the only variable it uses to generate the random number. So there's no dependency between the threads.
So it guarantees that one pair from and to account can be only acquired by one thread at a time?
So it's just completely independent. So with normal rand, it has some state that each thread is accessing. So like within the call to rand, it would have a lock or something like that. So if there's 8 threads calling rand, there'd be a lock. So they kind of serialize a little bit, and it would be slower because of that. But if I use rand r, it only generates a random number based off that seed, and that's it. So it's completely independent now. So I don't have any data races because I'm the only thread doing it. So each thread has its own, whoops, where is it? Each thread has its own seed. So that's the state it uses to generate a random number. But yeah, so too big to fail. Yep.
I have a question. So since we have a mutex here, so only one thread can make like a bank transfer at a time.
Yep.
Then how is a multi-threading helpful here if you're just making one thread do going on?
Oh, so your question is, if I do this, why is it faster? Like when I have my lock and I'm actually using it?
Yeah.
So it's faster because there's a little bit of it that can be done in parallel. That securely connect to bank can be done in parallel.
Oh.
So that's a good question though. So if I actually just lock the entire transfer function, well, it's probably going to be really slow.
Oh, okay.
Yeah, so the comment is, wouldn't it be running the same time, just kind of crappy? It's been more than 11 seconds.
So I guess.
Yeah, so now instead of just doing single threaded where just one thread just blazes through it and goes as fast as possible, now it takes 25 seconds. So now there's an overhead with all of the threads. We're essentially just doing it all single threaded anyways. There's a lot of context switching. We're also decimating our caches, which is another consideration when you actually do like performance, programming for performance. So yeah, it's just not bad, which is why I have this securely connect to bank, because doing those like few math operations is so fast, parallelizing this just isn't even worth it. So that's why we have this securely connect to bank thing, just to waste some time. So here too, when I have this, can I put up? So I can also see that's kind of single thread by my CPU usage. So if I look at htop, I can see all my threads kind of fighting, but there's a big red column, which means they're kind of all waiting for a large amount of time, and then it finishes executing. So I can see just based off my CPU usage, kind of what's going on. So there's a lot of fighting there. They're trying to do a bunch of work, but it's not quite working. But I am hitting every single core. So I am using all my cores, which is good. So the kernel's doing its job. We're just kind of failing. All right, so can I do anything better than this? So this doesn't have data races. It works. It's correct, but slow. No one likes being slow. What's a better idea? More threads? Sorry?
So you divide the account by 8 and then just like instead of using like a random generator, you give it like chunks to work with.
I'm assuming it's all random. We can't change that. Sorry, back?
Instead of locking all accounts, can we lock only the account we are using right now?
So both the two accounts we're using?
Yeah.
Okay, is that what you're gonna say?
Just create a lock for every single account.
Okay, yeah.
We can move the lock after the division because it's a read, right? I think.
You want to move it here?
Oh wait, but what if that account gets something different?
Yeah, so is this a data race?
Yeah, because with from balance updates can preempt another data.
Yeah, you only need one write to happen at the same time of a read. So here, lots of reads could happen in parallel, but they don't stop a write from happening. A write could still happen, means there's still a data race, even if this is only a read. Yeah.
Does the division take a little bit of time?
Yeah.
Could we do like, can we just save from balance? Oh wait, is there a way to like save from balance and then do the division while all the threads are doing work? And then,
But they might update the balance before then, right?
it's all over.
It's all over. So we can't do this. This won't work. I mean, we can even run this. So not a too big to fail bank. Let's just do 100. So if we run this, we'll probably see that it is, okay. Hey, it worked. So this makes it a lot rarer. Oh, geez. It is not actually the solution. Oh. Come on. Okay, well, there still is a data race, which is why this stuff is hard. It's just not going to do. So let's do your suggestion, which is one lock per account. And yeah.
Before we do that, I have a question. Can we get the deadlock with this, or is that not possible?
So with this right now?
Yeah.
So yeah, that's a good question. Someone else answer. Can I get a deadlock here? No, there's only one lock. So I can't get a deadlock unless in like the dumb situation where I relock my own lock and deadlock myself. But aside from doing something silly, you don't have a deadlock here because there's only one lock, so you don't have hold and wait or no circular wait, unless you consider your, the self loop. So yeah, another question was, can you do a mutex only if two threads are accessing the same account? And that's essentially just having a mutex per thread. So we can change this account. We just add our mutex here. So pthread, mutex, t, mutex. All right, cool. Do I have a mutex now? I have to initialize it. Yeah, we have to initialize it. We have to be good citizens. So we should probably initialize it wherever we initialize starting balance. I'd use pthread mutex init. And then it needs a pointer, so it would be address of accounts I.mutex. And then its additional arguments are null because we don't care. So that works. We should also probably be good citizens. Where do I free? So let's set a good example here. And if we initialize the mutex, we should also destroy it. So we'll be good. Whoops. Oh, I think you just destroy straight up. Whoops. What the hell? Oh, it doesn't take a null. My bad. So it doesn't take another argument. I think that makes it happy. There. Now we're good. All right. So now we have a mutex per account, and we initialize them. So in our code, I now have a mutex per account, so I can get rid of this mutex. So what should I be locking? Yeah.
The mutex for the front and two accounts.
For both of them?
Yeah.
For both of them, okay. Do you care what order I do them in? No, don't care. So that's okay? To and from? Okay, so I'm still missing something. I should unlock them. So I should probably just unlock them. I'll just do them in reverse order. All right. Yeah.
Can't you just lock the from around the amount equals from balance divided by 10 and from balance minus equals amount, and then unlock it after that, and then lock the two, do the two balance plus equals, and then unlock it?
Like that? That seems like it should work. right? Why would that not work? Any reason why this wouldn't work? All right, well, let's just send it, see what happens. It worked. It's hella fast too. Is there a possibility of a deadlock here? No question mark?
I think we should like log the account with the smaller account number first, and then otherwise. Oh wait, no.
Yeah.
Like if the A thread just accidentally gets the same pair of from and to, and some of them are waiting on host from and waiting for to, and some of them host to and waiting for from. Is that a possibility?
So, I mean, there's a possibility that we have like, transfer B to A and then transfer A to B. So, but is there a deadlock in this case? So here we're going to have a lock A and then unlock A and then a lock B and unlock B. And in the other case, we're essentially just going to have lock B, lock A, unlock A. So is there a deadlock between these two? Oh, there's no circular wait or anything. I'm only holding, like one of the conditions is hold and wait. I'm never holding two locks simultaneously. And I also never have any data races. So this is actually the best solution that you could come up with that the other section did not get. But let's make it challenging on ourselves, because another thing we could do, we can overlock things and be fine. What if instead we do what the original solution was, which was this. Yeah, so is this deadlock? I get them in the same order every time, right? I always get from then to. So I shouldn't get yeah, but the locks are actually by pointers. So from and to don't always refer to the same locks. So in this case where I have transfer B to A, from is from's A, so it would get that lock first. So it would be lock A, lock B, followed by unlock B, unlock A, and then in this thread, we would be doing lock B, lock A, unlock B. So that's a possible deadlock, because this thread running transfer A to B could acquire the lock, and then we get context switched over to this thread. It could acquire lock B, and now we're holding each other hostage. So this thread here wants lock A that the other thread has, and the original thread wants lock B that the other thread has. So now we're at a deadlock. And to illustrate that, I'll just compile this, and if I run this, we should just sit here essentially forever. So let's let it time out. Okay, that's long enough. We can be reasonably confident at deadlocked. We can look at our CPU usage. They're all just sitting there kind of waiting around. Our CPU's not doing anything. Everything's just kind of all screwed up. So if we kill it, we killed it at 29 seconds. There's quite obviously a deadlock. So how would I fix them if I don't want to do our good solution? So if I want to keep acquiring two locks and hold two locks at the same time. Yeah, so ensure every time the order, which I think is what you said too. So one order I could do is just by, okay, I'm going to keep this for a second. So one order I could do is just all the account IDs are unique, so I could just check the account ID. So if from is less than 2 ID, well then I can create some variables, pthread mutex, pthread mutex pointer, call it M1, have very clever names. So M1 would be equal to from mutex. So I'll always get the lowest ID first. And then if this is not the case, then I will just swap the order. Whoops, holy crap, that's a lot from. So now I'm always getting the lowest lock first. So now if I have, so now I could just lock M1 and then M2. And then when I unlock it, I would do M2 and M1. So now is there a deadlock? No, because I get everything in the same order. If I have this situation again, well, I would have to assume, if I assume A has a lower account ID than B, then this transfer would not look like this anymore. It would have actually done lock A, lock B, and do it in the same order. So now here, we don't have a data race anymore because we don't have any circular dependencies. We're all in the same order. So if I do that, let's just sanity check with just 10 accounts. Did I screw up? Uh-oh. It's all over. Ruh-roh. What the hell did I do? Oh God, that's a bad example. It's M1, M2.
Aren't you still locking A, locking B, and then when you're like thread B, you're trying to lock something that's
Oh, this should be in the same order. So if it's A and B, they would be in some specific order. Did I screw up my IDs? From two. Oh, Christ.
Could that be like from account transfer to itself?
Oh, so yeah, that's what's happening. That's what we forgot. So because of this, because we have 2 locks now, thank you, that would have taken me forever. Now I could be in that double lock situation where I block myself, but that's kind of dumb. If I'm transferring to myself, why do I even have to calculate anything or do anything? It's net 0. Why would I bother transferring to myself? So I can also just speed it up and just say if from is 2, so the 2 pointers are the same, or I could check if the IDs are the same, it's going to mean the same thing. Then I just give up. Thank you for mentioning that. So now I'm good. So before I was deadlocking myself, now if I run this, it should run and it's fine. And it actually doesn't run that much slower. Okay, yeah.
Can you explain that? I'm so kind of confused on why this works.
So this works because the situation where we deadlocked, it was because it looked like this. So there was a possibility where it acquires lock A and then wants to get lock B, and then another thread gets lock B and then waits on lock A. So we eliminate that circular dependency if we always acquire locks in the same order. So in this case, because we check the ID and we always get the lowest ID first, and they're unique, this would never happen. We never try and get lock A before lock B. So it would look like this. And if it looks like that, then whoever gets lock A first will get lock B. Yeah. Okay. What's the second way I can fix this? If I don't want to do this because this looks kind of ugly. Yeah, well, I could. So this eliminates the circular weight, the circular dependencies. I could also eliminate hold and wait. So I could give up the lock. So instead of doing this, I could just go ahead and pthread mutex lock the from side. So if I acquire this lock, I don't want to hold on to the other lock. I would just want to try it. Just give it a little try. So pthread mutex try lock. So I could try to acquire the 2's mutex. And so the way try lock works is if try lock returns 0, it means you got the lock. So it would fall out of this loop if it actually acquired the 2's mutex, and then at this point it would have both mutexes. If it tried and it got it immediately, it wouldn't go into the while loop, so it would just fall out, and I would have had 2 mutexes. But if I go into the while loop, then I didn't get the lock. So what should I do? Yeah, first thing I need to do is release the lock, because I have to eliminate that hold and wait. I couldn't grab the other one, so I would just go ahead and unlock the from lock. So now I unlock it, and then here I should probably sleep or yield. You'd think there'd be something called this, but there's not, because the kernel doesn't really care. Sketch, I think. The kernel doesn't really care what you are. If you're like the original thread that started a process or like a kernel thread you created. So there's just a default term called schedule yield that just tells the scheduler, hey, I'll yield myself. And then before you try again, you want to reacquire the from mutex again. So before I try again, I want to make sure that I actually lock the from mutex again. So that way I try again, and the only way I fall out of this loop is at this point I have both locks. And that's, if I make it there, I want to make sure I have both locks, so that's why you have to relock again to get the from, and then you try again to get 2, and then go back and forth as many times as it takes. So here I need to unlock my locks. All right, so do I have a deadlock now? No, because I eliminated hold and wait. So if I execute this, it should work. Yay. Yeah.
So it's like if someone else grabs the from mutex after you finish yielding, you try to go in, but someone else already grabbed it, you're just waiting until they release it, right?
Yeah, you'll either, when you wake up from the yield and from's not taken anymore, you can grab it again, or if someone else did take it as part of like another transaction, you'd get stuck at the lock and wait for it to pass. And so you're just waiting for that lock. Okay, cool. I will, yeah.
So at that point, you still have the Q lock, right? Because you're still trying to. So when you're trying to try the Q lock, is it within the same thread, or is it like another thread doing it, or is it?
So the question is like, don't I have the 2 lock when I go to sleep? Maybe.
Yeah.
So, oh, cool. My camera died. So in that case here, if I go into this while loop, it means I did not acquire the 2 lock because it failed. And then right before I sleep, I unlock from. So at this point, I have no locks. So I only sleep when I hold nothing. And then I only make it out if I have both. Yeah, so another cool thing real quick is so debugging this things are kind of hard and almost borderline impossible. But what you can do is there is this fun little thing called fsanitize thread that you can compile your program with. So in this case, I know I have a deadlock, and if I run this, it will actually give me some useful output and kind of yell at me. So this is like a tool you could use where it says, hey, mutex M0 is acquired while holding M4. So that's telling you you have a hold and wait condition, which means you have a possibility of a deadlock. And that's really the only thing, aside from reading the code, that will help you debug it. So that's it. That's pretty cool.
Is this like in any scenario when we're doing those to reduce the case of not data racing? Can we just like suppose we use the mutex block? Can we use like 7 for all condition variable to solve the same problems?
Yeah, you could. It's just going to be a lot less readable. All right. Well, just remember, I'm pulling for you.